Hello, my name is Indrapreet Binning and my technical advisor is Dr. Wang. My project is titled Improving the Mechanical Performance of 3D Printed Parts Using Fused Filament Fabrication. For this presentation, I'll walk you through my entire senior project. We'll first start with how the senior project idea developed, then go into an introduction to fused filament fabrication, the problem statement, industry solutions, proposed process, experimentation, and then finally the conclusion. This senior project was chosen because of my interest in 3D printing and applied statistics. I approached Dr. Wang with senior project ideas involving 3D printing, and he proposed this project since he thought it would be worth researching. So let's begin and talk about an introduction to fused filament fabrication. Fused filament fabrication is a technology used in 3D printing. It works by depositing filaments side by side on a print and then repeating this layer by layer until the print is completed. The animation on the right hand side does a very good job of showing this technology in action. Some of the advantages to fused filament fabrication is that it's relatively inexpensive, you get good resolution, and you have fast changeover. The disadvantages include the surface finish of the part, process variation, and the biggest drawback, which is mechanical performance. The mechanical performance is poor because the fused filament fabrication process is what you call anisotropic. What that means is that the strength of the part varies depending on how it is built. A good way to think about this is to compare a print with a piece of wood. Trying to cause a failure by applying a force along the grain of the wood or of the print would be extremely difficult. It would be much easier to create a failure by applying a force against the grain of the wood, or the print in this case. The term used for individual fibers on a print are called rasters. So to clarify, forces applied across rasters would cause a failure much earlier than forces applied along rasters. The problem that the 3D printing industry is facing is that in order to make 3D printing a technology that's used to manufacture on a larger scale, a solution needs to be produced that will improve the mechanical performance while also minimizing the total process time. One solution that industry has come up with for this problem is called resin infiltration. And this is where you would print whatever you wanted to create, and then afterwards you would coat it with a resin as seen in the picture, or you submerge it in a resin bath. The resin infiltrates the print between the rasters and then hardens. Effectively, what this is doing is it's creating stronger joints between rasters and adjacent layers in the print. The downfall, however, for this solution is that it takes a really long time for the print to cure. So the idea proposed by Dr. Wang is a new manufacturing process that would reduce or eliminate the air gap between rasters. So it's similar to what resin infiltration would do. The air gap would be reduced by using a high intensity lamp to center the layer, and hopefully the intensity will cause the rasters to soften and then create a better bond with the adjacent rasters and layers when it solidifies. This would create a homogeneous layer that would be less anisotropic. The process would begin by printing a single layer, then using a high-intensity lamp to flash it, and then you would print another layer, and then flash it again, and then you would repeat this process until the print is completed. So for this project, we'll pretty much be investigating, and in our case, we would be using a machine called a syntron, and that would act as our high-intensity lamp. It's seen in this image right here. This project is going to be focusing and investigating on to see if the syntron is able to reduce the gap between rasters. If it is, then we can move on to the proposed idea and see if it would be successful. So for the syntron, there is a lot of different factors that could be used for this experiment. But for this project, I decided to focus in on two important things, and that was the voltage and the number of pulses. So the first experiment that was done was to figure out what exactly the operating window was for these factors. So old parts were previously created were brought into the lab, and the number of pulses and the voltage setting were varied until there was a visual effect that I could see on the part itself. As we look on the slide, you can see these prints that we have here. And these images were white when I began the experiment, and the dark spots are pretty much burn marks on the surface of the print. The key takeaways that I got from this experiment was that contamination of oils and inks on the surface increases the likelihood of burns occurring. A high voltage causes burns on the surface, and a high number of pulses coupled with low voltage creates a smooth surface on the part. So from this, we got the operating window, which was somewhere around 10 to 20 for the number of pulses, and then 1600 to 2350 volts for the voltage. After the operating window was established, another experiment was conducted. This was done with the help of Sam Vieira, and the purpose of this project was to determine the effects of the syntron on the layer height and on the height of a neck if we were to look at the cross-section. The idea behind this project was to apply different treatments on the parts and then use a microscope to look at the cross-section. So once again, the response was the height of the top layer itself and then the height of the necking that we hoped would occur between the rasters. So this experiment had two factors, which was number of pulses and voltage, and a sample size of 2 was chosen because of time constraints. The table on the slide shows us each treatment and the settings of each factor. 4 levels were chosen because we didn't want to risk the chance of missing the operating window and getting a result that was very misleading. We took our learnings from the trial experiment, and so we tried to make this experiment as highly controlled as possible. From the manufacturing process to the exposure process, gloves were worn at all times. Treatment order was also randomized on jump, and after the prints were exposed, they were labeled with the treatments. For the measurement process, the parts were cut with a scalpel. The cut was made perpendicular to the raster, and then a portable microscope was used to measure the layer height and the neck height. After that, we kind of ran into an issue with this experiment. So the portable microscope itself was not able to determine the exact magnification at each setting. So a decision was made to standardize the response by taking a ratio between the layer height and the neck height so that we could compare each and every single image to one another. So the data analysis, what it revealed is that a lot of noise was present in the experiment. The R-squared value for the experiment was 0.07, I believe, indicating that the model wasn't very useful. With this in mind, the analysis continued, and the p-value for the main effects of each factor and the effects of the interaction were not significant. However, the syntron did have a physical effect on the part. So if we look at this image right here, this is a cross-section of one of the prints that was created. As you can see, from the bottom layer all the way to the top, you'll notice that there is kind of like a curvature, and it's not supposed to have that curvature. It should be a square, so it should be flat. We saw this occur when the treatment was on the high setting for both factors. So we then decided that maybe we should use some sort of different tool to measure instead of the portable microscope. So Dr. Wang informed me that there was a scanning electron microscope in the microelectronics lab. I contacted Dr. Richard Savage from the biomedical engineering department for assistance in using the SEM. I told him about my project, and we decided to look at one sample first and see if the SEM would be appropriate for my use. So in order to use the SEM, you need a conductive surface. My prints were ABS, so we had to use a sputtering machine to coat the surface of the cross-section in gold. After the surface was coated, the sample was inserted into the SEM. The image of the cross-section revealed that the SEM would do a good job of getting us an image of the cross-section. So the next week, 4 more samples were brought into the lab. This table lists the samples that were chosen. The low treatment, the 2 medium treatments, and a high treatment were chosen. From these samples, we would be able to compare the samples against each other and determine if the syntron was successful in reducing the gap between rasters. The image on the slide shows the cross-section for each one of the samples. We can see that there is still a gap between rasters regardless of the treatment. At this point, all of the evidence supported that the syntron is not successful in reducing the gap between layers. Another experiment was conducted to investigate the effects of the syntron on solid parts. The samples from the last experiment were not 100% solid, and that's what we believed caused a buckling or warping because of this. 3 samples were printed, 1 was kept as a control, and the other 2 were exposed to the high treatment. During exposure, the samples experienced warping once again, and can be seen in the before and after picture of the exposure. 1 sample also had a burn mark on the surface. Eric Beaton from the Materials Engineering Department was contacted to get access to an optical microscope. The sample with the burn mark was not used because of potential noise it could have added to the experiment. The control sample and the treatment sample images were examined side by side. The treatment sample looked completely smooth, but after careful inspection we found out that the image might be misleading. The sample was brought back into the lab, and a polishing wheel was used to clean the cross-section of the print. It was re-examined under the microscope, and the new image was much more clear. Visually from the image, we can see that the air gap seems to be reduced, which was a turning point for the project since all the previous data did not support this. One last experiment was conducted for this project. This experiment would be able to compare the raster to raster gap across two sample groups. One group was a control group where no treatment was applied. The other group was exposed to the syntron on the high treatment of 20 pulses and 2,350 volts. The response for this project was the area of the gap between rasters. After exposure, all samples were inspected under an optical microscope. 4 locations on each part were measured and recorded, and a sample size of 7 was used for this project, or for this experiment. The data were then analyzed in JUMP using a one-way ANOVA. The assumptions for ANOVA were checked prior to use, and no major violations were made to that assumption. The box plot reveals that the variation in both sample groups is very similar if we were to remove the outlier in the control sample. The treatment sample group had a smaller average mean. The ANOVA table gives us a p-value which was greater than 0.05, so we couldn't conclude that the sample groups were statistically different from one another. In conclusion, the syntron was able to heat up the surface layer of the print, but the syntron was not successful in reducing the gap between rasters. All of the experiments concluded this result. If this project were successful in reducing the gap, it would have had a significant impact on the 3D printing industry. Instead of waiting for parts to cure, such as with resin infiltration, parts could be printed and used right away with strengths, with creating parts that are very strong. Prints could also be created watertight, which would have transformed many industries involved with machine repair. To end this presentation, I want to give a thank you to Dr. Wang for helping me with this project and giving me guidance, Dr. Rong, Dr. Kathy Chen, Dr. Richard Savage, and Eric Beaton for taking the time to help me with my senior project. This concludes my senior project.